Hello, my name is Catherine Romano. I'm a nuclear physicist working in the Nuclear Materials Processing Group in the Fuel Cycle and Isotope Division at Oak Ridge National Lab. I'm going to talk to you today about destructive and non-destructive analysis of spent fuel for IAEA safeguards. A little bit about myself. I received my undergraduate Bachelor of Science in Aerospace Engineering from the University of Southern California. And then I stayed home with and raised my family and went back to school and received my PhD in nuclear engineering and science from Rensselaer Polytechnic Institute. And I've been at Oak Ridge for 2 years now, about 2.5 years, working in spent fuel measurements and at the Radiochemical Engineering Development Center. So what I'm going to talk to you today is the IAEA safeguards for spent fuel measurements. And why do we measure spent fuel, what the current measurement techniques are, and some of the new techniques being examined. And I'll give you an example of a couple of the Neutron techniques, ones that I'm familiar with, and relate those to some of the things that we're looking at for the future. So why measure spent fuel? Well, first of all, the IAEA wants to verify operator declarations of burnup, cooling time, and initial enrichment. We will measure spent fuel in case of loss of continuity of knowledge, in cases where there may be no operator declarations, and to check for diversion of material. We would do this at the input of a reprocessing facility or at the input of a repository or whenever fuel is moved. So what can a measurement tell you? It will give you measurements possibly, if we do enough of the proper types of measurements, it can give you initial enrichment using passive and active neutron measurements. Cooling time and burnup can be achieved through passive gamma and passive neutron measurements. And diversion is usually through a visual inspection, shrink-off radiation measurements, and active neutron interrogation. Plutonium content may be able to be determined, and that's one of the things that is being worked on now, is how to determine plutonium content in spent fuel assemblies. So I'm going to give you a little bit of history as to why we're investigating new techniques to measure spent fuel. Spent fuel input to reprocessing is based on an operator declaration. So the operator declares how much burnup and cooling time and initial enrichment, and then that is verified in the input accountability tank in the reprocessing facility. And it's based on calculated reactor data. So these values have always been accepted and used as a shipper-receiver evaluation. In other words, we look at what the shipper declared and then what the receiver at the reprocessing facility measures and determine that, that the shipper declarations were accurate. And there was really no verification or validation of the shipper's declaration as far as the IAEA was concerned, as long as it was within a certain quantity. So let me get all this animation up here. So as you can see, at the input of a reprocessing facility, down at the bottom here, the fuel, and I'm trying to get my pointer. We have a shear and dissolve, and it's put into the input accountability tank. So the fuel assembly is chopped up and dissolved in this input accountability tank. Samples are taken, and then the waste measurement is taken, and an oxide production measurement is taken. So you measure the input, and you measure all the outputs of the reprocessing facility. So this really wasn't a problem for a while, the fact that there was a shipper-receiver difference, a small amount. But it's been going on for about 40 years in reprocessing facilities. And historically, there's been a 5 to 7% bias in the plutonium content. So the shipper declarations were too high. And we're not really sure where that, why that is so. And this has come to the attention of IAEA and also here in the United States, when we're trying to determine if we want to reprocess and we want to safeguard our spent fuel. So the attention came to the shipper-receiver difference came about when in Japan there was a cumulative difference that reached 206 kilograms of plutonium. So the shippers had declared over the years more than 206 kilograms of plutonium, higher than was measured in the input accountability vessels at the reprocessing facility. And we also had a similar experience at West Valley Reprocessing Facility here in the United States. So what is the cause of the shipper-receiver difference? And that's something that we at Oak Ridge have been looking at, and I'll discuss that a little bit later. But basically what we believe it is that the operator declaration does not take into account the axial profile of the burnup of the fuel. So as you can see here, this is a fuel rod, and it's a gamma scan of the fuel rod. And you can see at the ends, the gamma counts decrease, and that's a measure of the burnup. So in other words, there's less plutonium down on the ends of the fuel rods. And this could account for the difference in plutonium between what the shipper declares. Because basically, the stated burnup for an operator is generally right along this top line here. They take an average burnup, and there's not really an accountability for this decrease along the edges. Now this may not be a problem in the future because our simulation capabilities are improving greatly, our computational capabilities. So what the reactor operators are working on now is to increase the fidelity of their simulations, and they may be able to now account for this axial burnup in their shipper declarations. So what I'm going to talk about now is a little bit about what does the IAEA currently measure in spent fuel. And most of the time, the IAEA relies on operator declarations. And that is reported to the IAEA, and the IAEA will go out and verify that, but mostly by reviewing records. But sometimes when the records don't match what they're expecting, or on a random basis, they'll come out and use, most commonly, a fork detector. And a fork detector measures the passive gamma activity and the neutron activity. So it's a gross gamma count and a gross neutron count. And it uses ionization chambers to measure the neutrons and the gammas. So this is mostly to determine gross defects. So they can get a general idea of are the operator declarations accurate to within, say, 10%, and then it's a comparison between fuel assemblies. So all the assemblies that are from the same reactor and burn the same should all look the same, basically, to the fork detector. So here's a picture. The picture on the left, you can see a fuel assembly being pulled up in the spent fuel pool. And the fork detector, if I can get my pointer, this is the fork detector right here around the fuel assembly. Here's the fuel assembly. And it's taking a measurement in the spent fuel pool. And here is a drawing of the same thing. Another device that is used by the IAEA is Cherenkov radiation viewing device. And what that does is it amplifies the light that is given off by Cherenkov radiation. And Cherenkov radiation is a blue glow in the water that's caused by the gamma rays being emitted from the fuel. And what you can see here, these are actually fuel assemblies from our high flux isotope reactor at Oak Ridge, and you can see the blue glow. And they use this device here, which is a viewing device that amplifies the light, and they can determine if there's a gross defect in the fuel. So what they're looking for in a reactor mostly is missing fuel pins. Now, as far as destructive analysis, they use in reprocessing facilities what's called a hybrid K-edge XRF analyzer. And this is an interesting piece of equipment, and it's very useful. It's used at the input accountability vessel at a reprocessing facility. So once the dissolved fuel is mixed and homogenized in the input accountability vessel, they will take several samples and use the hybrid K-edge to analyze those samples. They will use the hybrid K-edge for 100% of their samples, and then 10% of those samples will then go on and be sent out for mass spectroscopy, which is a destructive analysis, and that's also very accurate. And this is done at the input accountability vessel, and it's also done in the plutonium stream. So the plutonium is purified and comes out as a plutonium nitrate, and those samples will also be put into the hybrid K-edge, and some will also be sent out for mass spectroscopy. So the hybrid K-edge consists of a 160 kilovolt X-ray generator, and you can see the X-ray tube is right here, and two high purity germanium detectors. One here. Here's your sample in red, and another high purity germanium detector here. And what it does is it identifies and measures concentrations of solution containing heavy elements. So it will measure the concentration of plutonium and uranium, and sometimes curium, and it will give you the ratios of the concentrations of each. And the accuracy can be to 0.1%. So if you see the X-ray tube here, the X-rays go into the sample, and there's a transmission measurement. So the sample will absorb some of the X-rays, and then the detector will detect all the X-rays that are transmitted. And this other detector, what happens is the X-rays produce X-ray fluorescence, and I'll explain what that is in a minute, within the sample, and then and those will be emitted isotropically, but some of those will go down the collimator and be detected by the germanium detector. So we actually have now a hybrid K-edge analyzer at Oak Ridge, so I'll give you a little bit more detail. This is what it looks like in this picture, the top left. And we have made calibration standards at Oak Ridge, and here is one of our chemists taking some uranium from a nitrate solution and measuring it to put into one of the hybrid K-edge vials. So these are samples of our hybrid K-edge vials with uranium and plutonium solution, and then we place that vial inside the X-ray, the XRF, I'm sorry, the hybrid K-edge equipment. So what do we see when we measure? So what we look at is first we measure the concentration of the heavy element, and that is determined by how much of the X-rays are absorbed. So what happens is you get, if you look at this black line here, this is with no heavy elements in the solution in the hybrid K-edge vial. And this edge here is an absorption of the X-rays in the K shell of the atom. And so this line here, the height of this line will actually tell you how much was absorbed, and it will give you the concentration. So here's the algorithm. Here's the K-edge right here, and the change in the number of X-rays that are detected by the detector. And so we take this region here and this region here and calculate the difference, and that gives us the height of the K-edge. We also measure the XRF, and X-ray fluorescence is when the X-rays are emitted from the X-ray tube, they will collide with some of the electrons in the heavy elements and knock out the electrons in either the K shell or the L shell. And those will then be replaced by outer shell electrons. And when that happens, the atom will actually emit characteristic energy X-rays. So here is an X-ray spectrum. This is not a spectrum measured by the hybrid K-edge, but this shows you the peaks. This is a uranium peak, this is a uranium peak, and down here are plutonium peaks. And we use the ratio of those peak heights to determine the ratio of the heavy elements in the solution. So I'm going to move on to some of the new methods being investigated and focus on some of the ones that I'm most familiar with and go into a little bit more depth. But what we are trying to do is, as I talked about before, most of what we have measured, or what the IAEA measures now, is dependent upon operator declarations of burnup, cooling time, and initial enrichment. And what we want to do is we want to be able to better and more accurately determine the burnup, cooling time, and initial enrichment without operator declarations. And also, in addition, reduce the shipper-receiver difference. And also measure fissile content or plutonium content. And that gets more and more complicated. So one of the simplest ways to get a lot of information from the spent fuel is to use passive gamma spectroscopy. So the idea would be, if you can see this picture here, here's a spent fuel assembly, and it's being pulled up out of the spent fuel pool with a gamma detector and a collimator. And we would measure the gamma spectrum along the axial profile of the fuel assembly. And what you get here, and this is a plot of cesium-134 peak and the cesium-137 peak as detected by the germanium detector. And we could take several gamma spectroscopy measurements along the fuel, determine the axial profile, and then better determine the burnup. Okay? Instead of taking the average across the center of the fuel assembly. So I'll talk a little bit about how we are examining that idea at Oak Ridge. We had some fuel available at Oak Ridge to measure. Now they're just fuel pins, not entire fuel assemblies, but you basically can get the same information. And what I'm going to talk about is some 3 Mile Island spent fuel, and we're going to be looking at this fuel rod right here, the D5 fuel rod. And we have an operating history, initial enrichment, and this would be similar to what an operator would declare, your cycles of irradiation and cool down, irradiation and cool down. So what we did, we have spent fuel in a hot cell. So you can see here, this is the spent fuel, this yellow picture. We're looking through a glass that's filled with mineral oil and for shielding. And you can see the fuel rod and the rod positioning system. And here's our collimator here that goes through the hot cell wall. So this, in a reprocessing facility or a measurement facility, this is the same way that it would be done outside of the fuel pool if we were doing an entire assembly. But what we're looking at is just a single rod. And down here is our positioning system, and we use that for various number of fuel measurements, including looking at clouding and the size of the cladding and expansion and fuel characteristics. Here's our collimator. And here is an example of our gamma, an actual gamma measurement. So in the red, these are the isotopes that you can see, the fission products. mostly europium-154, cesium-134, and cesium-137. The fuel is about 15 years old. So, so these are the easiest to measure. Now, the predicted in blue is based on simulations. And as you can see, that's pretty close. We do get some cobalt-60 from some activation in the, there, right here. You get some cobalt-60 that's not in the simulation, and that's because that's activation of the clouding. So this is some of our spectra. We found that we can actually see self-induced XRF in the fuel. So I told you what X-ray fluorescence, how that was caused by the interrogating X-rays in the hybrid K-edge, but also the spent fuel emits so many gamma rays and beta particles that it actually creates XRF within the fuel. So we can see some of these peaks. Here's a uranium peak, here's a plutonium peak. This is an X-ray from europium-155, and a couple more of your uranium peaks. And this was the first time that XRF has been measured in solid spent fuel before. And then we also get our gamma spectrum. So here's your cesium-137, and this is why this one is always measured, because it's easy to see, and cesium-134. I think this is mislabeled here. So we'll go on. And what we're going to do, this is basically a plot of total counts along a fuel rod. And we've selected places here, this location, and this location, and we're going to send that in for destructive analysis. So basically, how do we know what we measured? And so what we do is we take samples of the fuel, and we do destructive analysis, do mass spectroscopy, and measure chemically how much cesium is in the fuel and how much plutonium, and compare that to our measurements. But what we also do is compare it to our simulations, and I'll explain that a little bit more. So basically what we do is we take ratios of the fission peaks. So we want to take ratios of how much of each fission product is in the fuel. And the more fission products we look at, the more we can determine about the fuel. For example, most commonly used is the cesium-134 to cesium-137 peak ratios. And so that gives you a ratio of the 134 to 137 content in the fuel. And that quantity is actually proportional to the flux in the fuel. So the flux in the reactor, I'm sorry, which then is in turn proportional to the burnup. So it tells us a lot about the fuel. What's really interesting is the cesium-134 actually is not created directly from fission. It's cesium-133 is created directly from fission, and then the cesium-133 has to absorb what's called an epithermal neutron, which is a little bit higher energy than the neutron that causes fission. And the epithermal neutron is absorbed by the 133, and it creates cesium-134. So that tells us a little bit about the flux within the fuel. So what we have to do then is do some correlations to burnup. And we do some simulations to determine, to compare our measurements to what we would expect to see coming out of the fuel, and make sure that basically what it'll tell us is how much cesium-134 and 137 are in the fuel when we compare it to a simulation. And what we did was we ran several burnup calculations, determined the cesium-134 to 137 ratios based on the calculations, and created a plot. And so now we can take this calibration plot and say, okay, until we get up to about 60,000 megawatt days, we've got a linear relationship between the burnup in the fuel and the cesium ratio. Okay, so what we can do is once we establish a calibration plot for a certain type of fuel, we can come back to this calibration plot, And let's say we measured a 0.4 ratio of cesium-134 to 137. We come over here, and we can say we were burned for about, say, 47,000 megawatt days. And I had mentioned using several fission product ratios. Here in the red, you can see the ruthenium 106 to cesium 137 axial profile. And what this tells you possibly is how much plutonium is fissioning versus how much uranium is fissioning, because the ruthenium 136 is produced 10 times more often in the fission of plutonium than in the fission of uranium. And so it's one more piece of the puzzle, along with other information, that we can use to determine how much plutonium is in the fuel. So you can see this red on the axial profile. And if you're looking at plutonium fission, you can see this drops down near the ends, which means, and it's not very sensitive to the amount of plutonium, but it does give you a little bit of information that the plutonium is decreased along the axial profile. And here is the fission mass distribution. So this is a distribution of the mass of the fission products created during fission for uranium-235, which is in red, and plutonium-239. And you can see ruthenium-106 would be right about here. And you can see for uranium, this is the amount produced, way less than 1%, about 0.1% of a yield. And then you come up to plutonium, and you're well into about 5% here. So this is one of the things that we're using to determine how much plutonium is in the fuel, is what fission products are in the fuel. So, and I'll move on to the X-ray fluorescence measurement. And again, this is almost a repeat of the slide that I showed for the hybrid K-edge. The gamma and beta decay in the fuel produce the XRF peaks, and here's the spectrum that I had showed you before, but this is actually from the fuel. And we take a look at this uranium peak. This is the K-alpha 1 peak, and then plutonium, which is this tiny peak right here. But we have a nice flat background, and if we take a long enough measurement, we can get a good calculation of the number of counts under the peak. And so we can take the ratio of those two peaks and determine the plutonium to uranium ratio in the fuel, which is, again, another piece of the puzzle that we use to piece together and determine how much fissile content and how much plutonium is actually in the fuel. And part of what we did was, if you're familiar with spent fuel, you realize that most of the plutonium is produced on the outer surface of the fuel pellet, which will skew our results. So as you can see here in this plot, this is the, the bottom plot. This is how much, this is the radial profile of the fuel pellet. So here's the center of the fuel pellet, and then here's the outer edge. And what you're seeing on the y-axis is the amount of plutonium in the fuel based on simulation, which means we're basically just measuring this outer portion when we look at our XRF spectrum. So what we're measuring is the plutonium to uranium ratio right on this outer edge of the fuel. Any of the XRF that is produced deeper into the fuel, we can't measure because it's attenuated before it reaches the detector. So we decided, we did some simulations and determined a correlation between the plutonium to uranium concentration in the fuel, in the entire pellet, throughout the radial profile, and related that to the measured plutonium to uranium peaks. And as you can see, we get, with some error, a straight line correlation. So it is possible. It just is a matter of creating these calibration curves, which requires many measurements and a lot of destructive analysis. And what I'm going to talk about now is what we do for destructive analysis. And at Oak Ridge, we have an analytical lab, and we validate our measurements and our simulations using destructive analysis of the spent fuel. So we also do a lot of work validating operator declarations and validating our burnup codes using destructive analysis. So we chose some destructive analysis segments, which I showed you earlier along the axial profile of the fuel. And then this is some of the results that we get. And this would be typical of the type of measurements that the IAEA would do when they take samples from the input accountability vessel in a reprocessing facility. So we can get the uranium, plutonium, isotopes curium and americium isotopes, and then the important ones for safeguards. Cesium, which gives us burnup information, neodymium, which for destructive analysis is one of the most important isotopes for burnup validation, europium, and gadolinium. These are most of what we can see. We can see ruthenium 106 here, and sometimes we can see cerium, and we also see 154 in our measurements. So these are things that we want to compare to. So what we did was we measured some fuel from Calvert Cliffs as well. And I have to put preliminary up there because we did not get the final results from our destructive analysis. But we did some XRF measurements of the fuel, and then we sent in the sample at the same location for destructive analysis. And so the destructive analysis plutonium to uranium ratio was 0.01, about 0.014, but what we measured was 0.02. And as you remember, that's because we're measuring this outer section of the fuel when we do our XRF measurement. So the calibration of this is going to be very difficult, but it is the only direct measurement of plutonium in spent fuel. All others are implied based on other measurements of other isotopes. So we also did destructive analysis of some MOX fuel. So, and as you can see, our measured values are very close to our destructive analysis values. So, you know, what's going on with that? Why are we measuring the same as the destructive analysis when we know the plutonium is actually built up on the outer surface of the fuel pellet? Well, in MOX fuel, because there's plutonium in the fuel from the very beginning, the plutonium content near the outer edge of the fuel, the outer portion of the radius of the pellet, tends to stay pretty stable. So what happens here, and these are several isotopes. So this is plutonium-242. 241 is here. Plutonium-240 is the circles, and plutonium-239 is here. And you can see this isn't symmetric, which means that this might be a fuel rod that was located at the outer edge of an assembly. So it's seeing different flux profiles. But what you can see is if you add all this up, it's kind of pretty much a straight line. And the plutonium content on the outer edge of the fuel is not much different than that in the center of the fuel. So again, all MOX fuel is different. It's burned differently and produced differently, and so the axial profiles will be different, which complicates the XRF measurement a little bit more. So, so now we're going to go on to, now we take all these measurements, how do we determine initial enrichment, burnup, and cooling time? Well, we use a burnup code. We use simulations. So we use a burnup code. Origin, which is developed at Oak Ridge, is basically the preeminent burnup and decay code in the world. And it tracks over 2,200 nuclides and fission products and reactions. So it's based on NDEF 7. and it can calculate time-dependent isotopic concentrations and the radioactivity of the spent fuel. And then we take a code called in-depth, which can actually take our gamma measurements or any other measurement results, run several origin calculations, and determine and kind of do a backwards calculation to determine what the initial enrichment, burnup, and cooling time was. What we found, though, is that from a gamma measurement, you cannot determine the initial enrichment in the older fuel. Maybe very fresh fuel, you may be able to determine the initial enrichment, but the older fuel, you need one more piece of information to determine the initial enrichment. So the in-depth takes an origin output, which is this blue, red at the bottom. This is an origin calculated gamma spectrum from spent fuel. And here's the same spent fuel, the actual measurement. So as you can see, we've got a lot of background here in our measurement, but you can see that the peaks are very similar and are well predicted. So we use these inverse calculations to try and backtrack and determine the burnup. So here is using cesium ratios in the red, and then in-depth inverse code here, case 1, where we're trying to determine both the irradiation and the decay time. And then in black, we're just trying to determine the irradiation time. So we're getting fairly close with those inverse calculations. But really, how close can we get to the real answer? And this is the big problem. How close can we get? We can take all the measurements we want. How close can we really get to determining plutonium content and determining burnup without operator declarations? So we had a student, actually, who did some of these calculations. And what he did was he found that if we could determine to within 5% the amount of curium-244, cesium-134, and europium-154 in the spent fuel, that we could determine the plutonium mass to within 1%. But the hard part is knowing exactly how much of these isotopes are in the fuel without destructive analysis. So if we know the cesium ratios and the europium-154, or I'm sorry, the absolute values of cesium-137, 134, and europium-154, so this is not ratios, this is knowing the absolute values. This is how many spent fuel assemblies will have the same answer. So we really can't pin down very well what the initial enrichment, burnup, and cooling time is for these assemblies. So you see cooling time is here on the left, and we're within a year for cooling time. That's the easy one. The burnup, we're within 4 gigawatt days, and the initial enrichment from 3.5% to 5% initial enrichment. That gives a lot of variation in plutonium content. So basically, we need to do more than just the gamma spectroscopy and passive neutron measurements to determine how much plutonium is in the spent fuel. So we're talking about how good can we actually get. Well, every measurement relies on a burnup calculation to determine the burnup, initial enrichment, and cooling time. So, and every simulation requires nuclear data. And this is one of the pieces of the puzzle that people forget. We have very, very accurate simulations. But that's assuming that we have perfect data. And we really don't. Our data leaves a lot to be desired. It's good, but it can get better. So here, this is a slide showing how important is nuclear data in the simulations. So here's some of the actinides, the americium. Well, here's curium-244. And we said that's one of the ones we need to know to get the initial enrichment. And here's the old NDF5, and now here's NDF7. So actually, it's a little bit less accurate in NDF7. And this is comparing the simulation to destructive analysis. But we're within 10%. And the cesium-134, there were a lot of, we underestimated cesium-134 by a great deal, by about 15% in our simulations. But here, in NDF7, that's been corrected, and now we're within 5%. These are very important things to know. How close can we get? Well, we could know we could know the content exactly in the spent fuel, but then you do the back calculation dependent on this nuclear data, and we could be off by 5 to 10%. So, so here's code benchmarks. This is comparing different simulation codes. You can see scale is here, and some of the ones you're more familiar with, MCMPX. And the measurement error was about plus or minus 3% for destructive analysis. And this is the difference between the destructive analysis and the simulation. Here's our plutoniums. Plutonium-239 is right here. So MCMPX was off by about 10%. And scale pretty much nailed it. And uranium-235, they're all under-predicting by about 4%. Plutonium-238 is a big problem, but that's not really used too much for safeguards calculations. What is the uncertainty in destructive analysis? Well, we can have an uncertainty in neptunium and curium-242 of about 10%. Depends on the lab. We have samples that go around to various labs, and there can be a large margin of error there. So basically, the best results is from multiple validation studies. So basically what I mean by that is you take an instrument, you measure it over and over and over again on fuel assemblies that are known, that you've done destructive analysis and you've done simulations, and you calibrate your instrument. Then when a fuel assembly comes through that instrument, that's an anomaly, you know that there's something wrong. So this is the type of thing that's done in the UK at their Thorpe facility. They have neutron measurements. They have passive gamma spectroscopy. Now they're measuring fairly spent fuel, but they measure all these fission products here, and they claim that they can determine initial enrichment, burnup, and cooling time. And they also do a passive neutron and an active interrogation using a californium-252 source. And it's basically a differential die-away method where you interrogate the fuel for a short period of time with neutrons and then measure how long it takes for the resulting fission neutrons to die away. And that will tell you something about the fissile content in the spent fuel. But one thing I wanted to mention about the Thorpe facility is in order to calibrate their instruments, they measured 7,000 fuel assemblies, known fuel assemblies with known operations. So that's how they were able to calibrate. And there's the big problem with the equipment that we're looking at now. Without an operator declaration and any history on the fuel, how can we use our instruments if they're not really calibrated for that fuel? We need something that can do that independently, and that's not easy. And I'll explain something about, a little bit more about the neutron measurements and what some of the difficulties are with those based on using an example. Here, again, this is the same slide I showed you earlier. This is Sweden, and they're looking at gamma spectroscopy along the axial profile of the fuel assemblies. And they determined that the maximum deviation from the measured and calculated burnup is about 8%. And they're using boiling water reactor assemblies here, so you can see the axial profile is very difficult. There's a huge change in the burnup along the axial profile. So I'm going to show you a little bit about an instrument that was examined and kind of put aside because it's something that's not very portable, so it's not really useful for the IAEA. But it's something that I'm very familiar with, and it'll give you an example of an active neutron interrogation technique and what the difficulties are with those types of techniques. So this is a lead slowing down spectrometer, and it was built in the 70s in order to measure spent fuel. And there actually was an operating lead slowing down spectrometer in Germany for a couple of years, and it measured single fuel pins, and I'll show you why that's a much easier way to go. And they could measure plutonium content to within 2% in the fuel pins. However, these now are looking at measuring entire fuel assemblies. So this is a lead spectrometer at Rensselaer Polytechnic Institute. Right here you can see the electron beam coming in. In the center of the lead spectrometer is a tantalum target where neutrons are produced using a gamma-N reaction. The electrons are at about 55 MeV when they hit the tantalum target. The spent fuel goes in a channel right here. And at one time, these channels here were automated to slide spent fuel through the lead spectrometer. Now this is about 6 foot on a side. It's 72 tons of lead. Here's our cooling system here. The gas goes through these tubes in a tub of water and then into the target to keep the target cooled, because lead has a low melting point, so we don't want the lead melting around the target. So here's a simulation of the lead spectrometer. So the red circles are the electrons coming in, creating the neutrons, and they bounce around in the lead and slow down and interrogate the fuel. So your fuel would probably be right about here. And we have flux monitors throughout the lead spectrometer to tell us what the flux is at any time. They're usually plutonium or plutonium-239 or uranium-235 fission chambers. And they'll tell us what the flux is in the lead. So what the simulation was here was that we would put a fuel assembly here, and I used a 16 by 16 fuel assembly and placed U-238 detectors across the top. So there are U-238 fission chambers. And what happens is the neutrons come in, the interrogation neutrons slow down. And as they slow down, they create fissions in the fuel, because as they slow down, they thermalize, and the thermal neutrons are really what create the fission in the uranium and plutonium in the fuel. The U-238 detectors measure only the fast neutrons, because they have they will not fission until a neutron is at least 1 MeV. So the fast fission neutrons come out and create a fission in the uranium-238 detector, and we measure only and these are pretty much blind to the interrogation neutrons, because those are lower energy, and we can determine the reaction rate in the spent fuel as a function of time. So what's interesting is basically this is the fission neutrons are, the interrogation neutrons are slowing down along the x-axis, and then here's the U-235 and the U-239 response, and this is the fission count, basically. So you can see the resonances in the fission reaction rate here for plutonium, and the same thing for uranium. So this gives us a lot of information. Now, can we figure out how much plutonium and uranium is in the fuel based on this information? So we divide this into sections of energy levels, of neutron energy levels. And you can see big difference here, 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 and here between the uranium and plutonium fission. Here's the uranium and plutonium, U-235 and plutonium-239 cross sections. You can see this big resonance here, and this is kind of, the x-axis is inverted here. Now your energy is going up along the x-axis. So this here, this is region 3. This is your big thermal resonance in plutonium, and that you can see right here. And this drops down because the neutrons start to die away once they thermalize. I'm going to skip this because I don't want to get too in-depth here. So basically, here's our neutron source, and I divided the fuel into 16 sections. And this is going to tell you, this is going to explain why neutron measurements are so difficult. And this is done in air. A lot of the measurements are proposed in water, which complicates matters even more because the neutrons thermalize quite a bit in water. So neutron source, this is your fuel assembly divided into 4x4 pin sections. So what we did was I looked at the fissions created in the fuel based on the neutron source. So as you can imagine, the fuel absorbs neutrons, and there's a lot of self-shielding created by the fuel assembly. So here, in purple, this is the fissions in the fuel in sections 1 through 16. Here's your neutron source coming in. And as you can see, this first section absorbs a lot of the neutrons, creates fission, but then there's self-shielding. And now you get about 20%, 30% of the fissions here compared to fissions here. So we don't get a uniform response throughout the fuel assembly. Now we look at the detector response. And what the detectors see is mostly the sections of the fuel that are closest to them. But what happens is, mostly because of geometric attenuation, the response in the detectors is very small from the furthest sections of the fuel. So now you have a nonlinear response to the interrogation neutrons and a nonlinear response of the U-238 detectors to the fissions in the fuel. So it makes it very difficult to deconvolute the answer. How do you figure that out? And the other problem is when you have spent fuel, now you have neutron absorbers in the fuel. How many neutrons absorbers are there in the fuel, and how many neutrons are being absorbed by the neutron absorbers? And this response changes as a function of the amount of plutonium and uranium in the fuel as well. So you've got a problem. And again, the best way to resolve that problem is by calibration. So basically, once you know how your detectors are going to respond to each type of fuel in this system, and you calibrate it using many, many fuel assemblies, then you'll know when you have an anomaly. So that's kind of the key. One thing active neutron interrogation is very good for, though, is determining missing fuel pins. So especially in the center of the fuel. So if you look at the center right here, we have 0.7% of the fuel missing. So we remove 2 fuel pins. But in region 2, when I showed you the different energy levels, region 2, the response changed by 26%. So you're only missing 0.7% of the fuel, but your detectors see a 26% difference in the response. So that's where an active neutron interrogation would be helpful. You can easily see missing fuel. And that is it. That's kind of an overview of spent fuel measurements and what the IAEA has done in the past and what they're looking at.